Hello class, welcome to day 4 of calculus. We're going to do compositions and inverses of functions, and we're going to look at some domain restrictions when we do things. So today's lesson, I put key. So let's talk about, we have two very simple functions, f and g, both are linear functions, so the domain for both of them are all real numbers. And let's see what happens when we do some simple things to them. So f plus g will just be f plus g is equal to 3x minus 1. And I don't think the domain has changed any. It's still all real numbers. Well, let's look at the second one. F minus g. Well, that's f minus, notice I have to put parentheses because I have to subtract the whole function. And I get negative x plus 5. And again, still a linear function. I don't think there's any domain restrictions. And then finally, the last one, I'm going to do f times g. And I'm going to get x plus 2, 2x minus 3, and I expand it out, 2x squared minus 3x plus 4x minus 6, and I get the nice quadratic 2x squared plus x minus 6, and again, with quadratics, there are no domain restrictions. So those were pretty easy. As opposed to looking at when we do multiplying and dividing. Well, let's look at these domains. The first one, oh, the square root rule. Oh, it's got to be -2 to infinity. There is a little bit of a restriction. And this one is just a linear function, so right now there's no restriction. But we'll have to see when we divide things out. So f over g is pretty easy. F is on top, g is on the bottom, and we get our function. But are there restrictions involved? Well, this one we know is -2 to infinity from what we said earlier, but this one has a restriction where x cannot equal 3. So we have to combine these together, and my domain for this one will be bracket -2 to 3, parentheses, union 3 to infinity. All real numbers greater than or equal to -2, but throwing out 3. Now we're going to do the other way. We're going to do g over f, or g divided by f, and g's on top, so that's x minus 3, and f's on the bottom, so that's a square root function. And again, if I look carefully at this, x minus 3 is in the numerator. There is no restriction. But this one on the bottom, oh yeah, when it's in the bottom, it can't be brackets anymore. It's -2 to infinity with the parentheses. So my domain for this whole thing is going to be parentheses -2 to infinity. Okay, so dealing with a few things, using some algebra, adding, subtracting, multiplying, dividing. And when we have this dividing one, you can see the domain may have different restrictions. Okay, now let's talk about compositions. We did it a couple days ago, but they were pretty basic. The idea of a composition is a function in a function. Well, sorry about that background noise. I can't control that. So coming back to the video, composition is a function inside of a function. Sometimes we use that open circle composition dot, and sometimes we just use the parentheses. We read it as f of g of x, or f composite g of x. The idea is that which one do you do first? You always do the one closer to the input first. So for this example on the bottom, I have two functions here, f and g, and I have to do g of 2 first, so g of 2. is equal to 2 squared minus 8 times 2 plus 2, and that is equal to negative 10. And I take that result and plug it in the f function, and 3 times negative 10 squared plus 5 times negative 10 minus 7, and that is 243. So f of g of 2 is equal to 243. This one I have to do f of 2 first, which is 2 squared plus 5 times 2 minus 7, which is equal to 15. G of 15 is next. 15 squared minus 8 times 15 plus 2, and that is equal to 107. So G of f of 2 is equal to 107. Notice, f of g of 2 does not equal g of f of 2. It should not. It would be a coincidence if it did. Order does matter with composition. Okay, those examples were with numbers and functions. Let's see it when we're just plugging functions in a function. So we have two functions. This domain we did earlier, negative 2 to infinity, and this domain we did earlier. There are no restrictions to all real numbers. So this one I have to do g first. So it's going to be f of g, which is x minus 3, and there's no restriction here. The domain is all real numbers still. But I'm going to plug that into the f function, and I get is going to be x minus 3 plus 2, all underneath the square root sign, and I clean it up. I get x minus 1 underneath the square root sign. And this has a domain restriction of 1 to infinity. All real numbers greater than or equal to 1. Now let's do it the other way around. F comes first, so I have to do g of the square root of x plus 2, and that does have a domain restriction of negative 2 to infinity. I'm going to plug that into the g function, so I get the square root of x plus 2, then minus 3, and there's no cleanup here, so my domain for the whole function is going to be negative 2 to infinity. Nothing has really changed. So now I'm working with decomposition. Decomposition is kind of like working in reverse. What do I need to do a composition to get what I want? So when I see this composition, I see it's g of h of x. That means first I do h, and then second I do g. So I look at this whole thing, and I realize, what would come first if I put a number in for x? I think the first thing I would do would maybe something like this. And then what do I need second that I would stick this function into? Well, maybe it would be e to the x, because if you look at this carefully, if you took this and put this for this x, you would get what you want. Also, I could have done it this way. Maybe h of x, I make this the 2x squared plus 1, and then g of x is not e to the x, it is e of the square root of x. So when I do this, it gives me what I want, because this is what I want. E to the square root of 2x squared plus 1. Now for this next example, it's the same thing I want, except I'm doing a three-part composition, g of h of m of x. So this is first, into here this is second, into here this is third, and maybe we get something like 2x squared plus 1, the square root of x, e to the x, because when I take this and plug it in here, I get the square root of 2x squared plus 1, and then when I plug it in here, I get what I want. Decomposition, breaking it up into pieces parts. So now we're going to talk about inverses. And inverses is when you switch x's and y's. And one way to do it is to reflect it over the line y equals x. Well, that line on this graph, the best I can do it with a stylus, is that line here, y equals x. And if I take this curvy little graph and reflect it over that diagonal line, I kind of get a graph that looks like this. So I know the original one in black is a function. Is that new one I drew in red? Is that a function? The answer is yes, because it does pass the vertical line test that you learned in Algebra 1 a long time ago, that if you pass a vertical line test, it's a function. But now I could do something called the horizontal line test that says if a function passes a horizontal line test, that means its inverse is also a function. So on this page, which one of the following graphs is a function whose inverse is also a function? Well, this one is good, and this one is good, and these are bad, because let's look at these tests. Definitely passes the vertical line test, and it passes the horizontal line test. Passes the vertical line test and the horizontal line test. Passes the vertical test, it does not pass the horizontal line test. And this one, the best I can draw, oh, it doesn't even pass the vertical line test. So this fails the horizontal line test, and this one fails the vertical line test. If a function has an inverse that is also a function, it is called a one-to-one function. Essentially, a function is for every x has exactly one y. Well, if the inverse is also a function, then that means every y has exactly one x. Exactly one x for one y for one x. We use special notation. If a function has an inverse that's a function, we use this special notation, f inverse of x, or the inverse function notation. So how do we find inverses? Well, the inverse is the undo of an operation. So when I had the 3x plus 2, which is multiplied by 3 and add 2, the inverse would be subtract 2 divided by 3. So how do I do with it? I have 4 basic steps. Step 1, rewrite it y equals. Step 2, switch x and y's. That's the inverse part. Step 3, solve for y. X minus 2 is equal to 3y. Step 3 still, y equals x minus 2 over 3. And then finally, step 4, using the inverse notation, in this case, there we go. That is, if this is the original function, this is the inverse of that function. It completely will undo that function. I have a couple examples here. The first one is very easy. It's like the example I did earlier. I just went through it. I switched x and y's right away. I didn't rewrite it. That's what I'm going to do here. This is the hard one. So if I rewrite this, it is x equals 2y minus 3 over 5y plus 2. Do not want to work with the denominator, so I'm going to put parentheses around this, and I'm going to multiply by 5y plus 2 on this side, and 5y plus 2 on that side. And what I'm going to do is distribute this x. I get 5xy plus 2x is equal to 2y minus 3, because these cancel out. Much easier. I want to isolate y. That means I want all the y's together on the same side of the problem. So what I'm going to do is, that has a y, it stays. This doesn't, it's going to move. This has a y, it's going to move. This doesn't, it stays. And I get 5xy minus 2y is equal to negative 2x minus 3, or negative 3 minus 2x, I don't care, it's the same thing. Now I can factor out a y. So if I take a y out of here, 5x minus 2 is left over inside the parentheses, and this does not change. And then I can divide by this. I use my notation. And I say h inverse of x is equal to negative 2x minus 3 over 5x minus 2. It was a complicated function to begin with, so its inverse is also complicated. So what is the purpose of an inverse? The purpose is to undo the original function, and the order doesn't matter. I don't care if you take f and put it in the inverse, or take the inverse and put inside of f. It doesn't matter. Everything will cancel out. You get x left over. So I'm going to do this one first, where I take the function and I put it inside the inverse. So it's f inverse of 3x plus 2 is equal to 3x plus 2 minus 2 all over 3. 2's cancel. I get 3x over 3. The 3's cancel. I get x. So I've just proven. This is a proof. This isn't finding the inverse. This is proving that they're inverses. A little bit different. I prove their inverses by showing that their composition together is equal to x. Everything canceled out. Now the other one I'm going to do the other way. I'm going to take this function and put it in for this x. So it's f of x minus 2 over 3 is equal to 3 x minus 2 over 3 plus 2. 3's cancel. I get x minus 2 plus 2. And the 2's cancel. And again, I get x. It shows you that it didn't matter if I did one inside the other. I got x either way because they completely undo each other. We did talk about symmetry the other day, and what's the difference between even and odd symmetry. One way is by looking at a graph, but another way is, you can look the same with tables or with equations. The idea is that if you notice here, one is a positive x, one is a negative x. So I have opposite x's. Let me erase that. I have opposite x's, but oops, get rid of that. Sorry about that. I have opposite x's, but these are the same outputs or y values. So these things in red are opposite. These things in red are opposite. So an even function, I have opposite x's, but I have the same output or y value. And for an odd functions, I have opposite x's, but then these are also opposites. Positive f here, negative f here means I have opposite x's and opposite y's. So how do we do this with a table? So f is even as g is odd. So even means opposite x gives me the same y value. So right here, this x is 1, this y is 6. So when this is negative 1, this still has to be positive 6 because they have to be the same. Negative 2x, negative 5y, positive 2 for x, still negative 5 for y, and then this would be negative 4. As opposed to odd, which is opposite x, opposite y, negative 1 has a y of 3, so positive 1 has a y of negative 3. 2, negative 1, negative 2, positive 1, and then negative 3, 2 gives me positive 3, negative 2. And then finally, I have to do this composition, which means first I have to do g of x, and then I have to do h of x. So if I'm going to start here, if I start here at negative 3, I'm going to finish up here in this block. So it says go to -3 and go to the g function first. And I did that, and I have 2. And then I have to do a brand new input of 2, which is here. And then I have to do f. Well, that f is -5. And I come here, back, way over here. I fill in the -5 right here. -3 input, G2 output, 2 input, -5 F output. That's my final results. If I do this for this whole table, I get this. So then my question is the final row, H, even or odd? And it's definitely even. H of the negative x values is exactly the same as H of the positive x values. Opposite x's give you the same y. Let's look at an example. We said f had to be even and g had to be odd, and I have to do the composition of h of x is f of g of x, which means g comes first, which is x cubed, but now I have to take that cube and do the f to it, which is squared, so I get h of x is x to the 6. That is an even function. That even function kind of takes over. Okay, again, we'll be on Zoom. Stop the video if you have questions. Ask me questions. We can go over stuff. Thank you again for listening.